For section 3.2, we're going to continue our study of predicates and quantified statements. In this case, we're going to start negating statements. So we're going to find that in our rules of negation, that negating quantified statements that have universal and existential quantifiers is very similar to negating statements that have disjunctions and conjunctions, ors and ands. If we consider the statement, all butterflies are pretty, how might we negate that statement? Well, we might say, not all butterflies are pretty. We might say, all butterflies are not pretty. Or I might come up with something else. These are just two examples of negations that students have come up with in the past in my classes. Which quantifier did we use here? Well, the implication is certainly right here in all. So if we remember, we used all, which is our universal quantifier. And remember, that is the one that looks like an upside down A. Well, how do we negate that quantifier? We're going to show falsity with at least one counterexample. And we negate, right? So we're going to negate that with one counterexample. Well, that means at least one butterfly is not pretty. So that would be some. Maybe some butterflies are not pretty. And this is leading us into the theorem that we have for how we negate universal statements. Our universal statement says, our theorem, 3.2.1 says, the negation of a statement of the form for all x in our domain, Q of x, is logically equivalent to the statement of the form there exists some x in our domain such that not Q of x. So what does that look like symbolically? This guy right here. So we negate a universal statement with an existential statement. Notice that our domain stays the same. And don't forget that when we have an existential, such that has to come with it. So notice that we negated the universal into an existential, kept the same domain, and then we negated our predicate statement, Q of x. And like I said, don't forget that there exists and such that are a pair. They always come together. So when we change our universal into an existential, we also have to include our such that. So that means that the negation of a universal is an existential. And we're going to find out in a little bit that the opposite is also true. The negation of an existential is a universal. Sounds very similar to the negation of a disjunction being a conjunction and the negation of a conjunction being a disjunction. Not and is an or, and not or is an and. So let's try applying this. So if I said in a previous section, we discussed how the statement for all real x, x squared is greater than or equal to x is false. How can we state its negation? Well, we want to negate the statement for all x in the set of real numbers, x squared is greater than or equal to x. And that, by our theorem, is going to be logically equivalent to, well, negate the universal into an existential. There exists some x. Keep the domain the same in the set of all real numbers. And remember, now it's an existential, so we got to bring along its partner such that. And now we have to negate X squared is greater than X. Well, remember that for our inequalities, we have greater, we have equals, and we have less. In our statement, we had greater than or equal, so our negation has to use, our negation has to use the less. So we would say then such that X squared is less than X. And that actually I gave you as a different problem. Let's try another one. For all triangles T, the sum of the angles in T is 180 degrees. So we're going to negate this statement, but let's convert it to a universal condition. So, or not conditional, sorry, a universal statement. For all triangles T, so for all triangles T, the sum of, or I guess we could say just for all T in this case, couldn't we? The sum of the angles in T is 180 degrees. Our logical equivalency here would be to change the universal into an existential. Say there exists some triangle T such that, and now negate the predicate. The sum of the angles in T, sum of the angles in T is not 180 degrees. So the negation of all is sum. And we're going to find out that this is going to go both ways. The negation of sum is all. Let's keep going with a couple more examples. So if I look at example C, for all prime numbers P, P is odd. So if we want to negate for all prime numbers P, P is odd. Well, let's negate the universal into an existential. There exists some prime number P. And remember, there exists has to include its partner, such that. And now let's negate the predicate. P is odd now becomes such that P is even. Or we could say P is not odd. So we could say either P is even, or we could say P is not odd. We're going to find out when we get into section 4.1 and 4.2 that our numbers our integers have to be either even or odd. They can't be both. Or neither. More of our cut and dry statements, right? The last example is a little tricky because this is implicit quantification here. Another implicit quantification. And on this one I said, no politicians are honest. Well, the other way to say that no politicians are honest is to say all politicians are not honest. So if we wanted to negate the statement all politicians are honest, or sorry, are not honest, we're going to negate that with an existential. Remember, the negation of all is some. So some politicians, and then we're going to negate the are not honest, and the negation of a not becomes an is. So some politicians are honest. So if we wanted to put it in Symbolic logic is say for all politicians P are not honest, or is not honest. If we wanted to say that P is not honest. And that negation would be there exists some politician P such that P is honest. However you want to state those. You can use more implicit quantification with some, or you can write it out with symbolic logic. And I know I've already said that the negation of an existential is not going to be universal, so we're going to go through and look at that. If I said, consider the statement, some mathematicians are talented musicians, we might actually pick up on the negation pretty quickly here, because we know that some is now going to get negated into all. So all mathematicians, right, we're going to make it into all mathematicians. Oh, I did not spell that well. Mathematicians, there we go. And now negate the predicate. Are talented musicians become are not talented musicians. By the way, it's an untruth statement. There's a definite link between math and music. I should know I have a music degree too. So we used our existential quantifier here, which is our existential. Existential quantifier. All right. And we're going to negate with the universal. Because we negate through the method of exhaustion for an existential. If we want to prove that it's not true, we have to prove that it's not true for all elements in our domain. That's the motivation behind our next theorem. Our next theorem says the negation of a statement of the form, there exists some x in our domain such that q of x is logically equivalent to a statement of the form for all x in our domain, not q of x. So symbolically, the negation of the existential is universal. So let's try using that on a few statements. There exists a triangle T such that the side lengths of T are 1, 2, and 5 inches. So we want to negate there exists a triangle T such that the side lengths of T are 1, 2, and 5 inches. And the negation of that statement would be logically equivalent to, well, negate the existential into a universal for all triangles T. And now remember, we lose the such that because such that is partnered only with there exists. Now we have the side lengths of T are 1, 2, and 5 inches as our predicate. We want to negate this predicate. So we say the side lengths of T are not 1, 2, and 5 inches. So the side lengths of T are not 1, 2, and 5 inches. And you know I wasn't going to let you out of this section without another implicit quantification. If I said some comedies are not funny, that is a true statement, and I will stand by this every time with the example of Nacho Libre. supposed to be a comedy, really not funny. So, it's one of the only times my husband and I definitely agreed on a comedy not really being funny. So we're going to negate our statement, some comedies are not funny, with the statement, all comedies, well, are not becomes are funny. So, kind of cool how that works. We negate a some with an all, we negate an all with a some. Example C is one of my favorites because it is from Doctor Who. So example C says, there exists a big ball such that it is made of wibbly wobbly timey-wimey stuff. If you ever want to see a really, really amazing episode of Doctor Who, this is from the episode called Blink. Believe it's in the second, maybe the third, I have to remember, of the new Who. So it's David Tennant is the Doctor here. It's called Blink. It's the first episode where the weeping angels come up. So there exists a big ball of timey-wimey stuff. So we want to negate there exists a big ball such that it is made of wibbly, wobbly, timey-wimey stuff. I am not writing all of that out. So we're going to negate there exists with a for all. So for all big balls, they are not made of wibbly, wobbly, timey-wimey stuff. It's something goofy that he says in the show. How about our last example here? I said some gamers are over 40. We want to negate the statement some gamers are over 40. We can negate that with the statement all gamers. And are over 40 we would negate with are not over 40. One of the most useful negations we're going to come across is this negation of the universal conditional. Because we're going to be able to use this at the end of chapter 4 as a means of indirect proof writing. We're going to spend the majority of chapter 4 proving statements directly, proving universal statements directly through universal modus ponens, which we're going to get to in section 3.4. But we've already seen modus ponens. It's essentially mixing a universal conditional with our argument forms. So we're going to be using that approach as our direct proof in all of chapter 4. However, there's another type of proof writing called a proof by contradiction, where we essentially try to prove the negation true. And what happens is we find out that if we try to prove the negation true, we come up against a contradiction. And when we come up against that contradiction, that means that our negation has to be false. So if our negation is false, then our statement was true. And we lean into that logic as a method of writing proof. So it's actually one of my more favorite ways to write proofs. I actually really enjoy proof by negations or proof by contradictions. So we're going to be looking at how to write out these negations. So we can actually derive the negation of a universal conditional based on information we already know. So if we're given a universal conditional statement for all x in our domain D, if P of x and Q of x, we can apply our first theorem, 3.2.1, in order to define the negation. So we'll negate for all x in our domain, if P of x, then Q of x, by saying, okay, well then that universal now becomes an existential. There exists some x in our domain D such that, and then we're going to have to negate the statement, so we're going to have to negate if P of x, then Q of x. So if we need to now negate the conditional statement, if P of x, then Q of x, remember that logical equivalency, the negation of P, if P of x, then Q of x is going to be the same as P of x and not Q of x. Remember that back from section 2.2, I think it was, the negation of if P then Q was P and not Q. It's not any different now that they're quantified statements. So how does that change our newly derived statement? Well, that means, okay, so then our negation of for all x in domain D, if P of x, then Q of x, now is going to become logically equivalent to, still there exists some x in domain D such that, and now let's negate the conditional, such that P of x and not Q of x. So pretty handy to use some of this logic that we already learned in chapter 2 and the theorem we learned earlier in this section to help us write a negation for the universal conditional. So we don't have an actual theorem for this one, but I did write it out for you here. I did say that the negation of for all x in D, if P of x and Q of x is logically equivalent to there exists some x in our domain D such that P of x and not Q of x. So let's try using our newly established negation of the universal conditional. So we have the statement for all integers z, if z is negative, then z squared is negative. So let's write it as universal conditional. So for all z in the set of integers, if z is less than 0, then z squared is less than 0. And let's negate that. And why did I put z is less than 0? Because that's what it means to be negative. It means to be a value that is less than 0. So now let's negate it. We start with negating the universal to an existential. Domain stays the same. The if then, if P then Q now becomes P and not Q. So we end up with there exists some z in the set of integers such that z is less than 0, right? P of z is true. Leave it as P of z and not Q of z. So not z squared being less than 0. And again, we have less, equal, and greater, and we only had less before, so now z squared has to be greater than or equal to 0. So we negated the universal with an existential. Domain stayed the same, such that has to be paired with that existential. We left P of z alone, changed the if then to an and q of z had to be negated. So z squared less than 0, the negation would be z squared is greater than or equal to 0. Let's try another one. For all x in the set of integers, if x is divisible by 5, then the ones digit of x is a 5 or a 0. So its negation would be there exists some x in the domain z such that p of x is going to be true, x is divisible by 5. So x is divisible by 5 and not q of x. So, and the ones digit of x is not a 5 or a 0. Well, is not a 5 and is not a 0. Right? Good old De Morgan's laws. If a computer program has more than 100,000 lines of code, then it contains a bug. So implied here is that a computer program implies all. So its negation would be some. So we would say there exists, right? There exists a computer program such that p of x is true. It has more than 100,000 lines of code such that it has more than 100,000 lines of code. And the if then becomes an and, not Q. It does not contain a bug. How about a little fun etymology behind the saying that it contains a bug? Back in the 60s, when we had computer mainframes that were the size of a room, they were literal bugs that would get into the system and would trip up the signals getting through. So they were referring to a literal bug in the program. So kind of fun there. Just a fun little tidbit. So I mentioned that there is a bit of a relationship here because the negation of a for all is a there exists, and the negation of a there exists is a for all. And again, I said that sounded awfully familiar to our De Morgan's laws that said the negation of an and is an or, and the negation of an or is an and. That similarity is not accidental. Universal statements can be seen as generalizations of and statements, and existential statements can be seen as generalizations of or statements. So it's not a mistake here, and it's not a coincidence that they are related. The last thing I wanted to cover in section 3.2 are variants of our universal conditional. So much like our conditional statements had contrapositives, inverses, and converses, our universal conditional also can have a contrapositive, a converse, and an inverse. And funny enough, they look exactly like their non-quantified counterparts. So these definitions should seem pretty familiar. If we have our conditional statement for all x in domain D, if p of x, then q of x, our contrapositive is for all x in our domain D, if not q of x, then not p of x. Our converse, remember, we're not logically equivalent to the contrapositive or the conditional. Our converse says for all x in our domain D, if q of x, then p of x. Putting the cart before the horse. Most common mistake I see students making when we write proofs. Doesn't happen often, but it does sometimes. Its inverse is for all x in our domain D, if not p of x, then not q of x. Also, still not logically equivalent to the conditional. So if the same equivalencies apply here, the universal conditional statement is still logically equivalent to its contrapositive. And the universal conditional statement is not logically equivalent to its converse or inverse. So not different from what we've done before. We just have them in a quantified form instead of statement form. So if I were to give you a statement and ask you to find the symbolic form of the universal conditional, and then its contrapositive, the converse, and the inverse, you should be able to do that for this one. Here I said if a real number is greater than 2, then its square is greater than 4. So we have a real number. That's our domain. So our domain would be for all, right? If a real number, remember there's our implicit quantification that implies all, for all x in the set of real numbers, if x is greater than 2, there's our q of x. If x, oops, I said q, I meant p. If x is greater than 2, then there's our q of x. Its square, x squared, is greater than 4. And here, our p of x is the statement x is greater than 2. Also, we could just say x is greater than 2. And our q of x is a statement that x squared is greater than 4. Or x squared is greater than 4 in this manner. So now we want its contrapositive. Remember, contrapositive says switch the order and negate them both. So our domain stays the same for all x in the set of real numbers. But now, if not q of x, so if x squared is not greater than 4, so if x squared is then less than or equal to 4, oops, I forgot the if. If x squared is less than or equal to 4, then not p of x. Well, that means x can't be greater than 2, so x must be less than or equal to 2. Remember, this is our for all x in the real numbers. If not q of x, then not p of x. Our converse says, oh, we just have to say if q of x, then p of x. We're switching them around. So for all x in our domain of real numbers, if q of x, so if x squared is greater than 4, then p of x, x is greater than 2. And we can see this wouldn't be logically equivalent because if x squared is greater than 4, well, x could be negative 3. Negative 3 squared is 9. That doesn't fit here. So we can see then this would be a false statement. So the converse, and we'll find the inverse, are both false. That's a pretty good sign because our symbolic statement, our universal conditional, and its contrapositive will be true. So let's also do the inverse. Our inverse says, oops, here I forgot to write in our standard form here. For the converse is if q of x, then p of x. And then our inverse would be for all x in the real numbers here. If not p of x, then not q of x. So we'll say for all x in a set of real numbers, if not p of x. So not x greater than 2, so x is less than or equal to 2, then not q of x. X squared is less than or equal to 4. And that's not true, because again, if x is less than or equal to 2, we could use -3. -3 squared is 9. 9 is not less than or equal to 4.